Hello, let's talk about the little ones today, the dwarf galaxies. What are some of their common types, their properties, and how similar are they to the giant galaxies? Let's begin. The term dwarf is often used to describe small or faint galaxies. While the low-mass galaxies are often faint relative to their more massive counterparts at the same redshift, vice versa may or may not be true. As I will show you today, sometimes large galaxies can also be faint. But in this video, we will primarily focus on the low-mass dwarf galaxies. Also, remember that whenever I say faint or low luminosity, I mean the intrinsic luminosity of the galaxy is less than the other galaxies at the same redshift, and not that it appears faint because it is too far. The low luminosity of dwarf is a limitation for observing them, and therefore most of what we know about these small systems is from our observations of the nearby universe. But with new large observing facilities coming up in the near future, we will be able to observe the dwarf galaxies in the distant and very distant universe as well. In an earlier video, we discussed about the morphological classification of galaxies. We now know that our own Milky Way is a barred spiral galaxy, and amongst the low-mass galaxies, the irregulars are the most common. Today, we'll learn a little bit more about some other type of dwarf galaxies and their properties. But before moving on to dwarfs, let's recall that our own galaxy Milky Way and most other spirals have a bulge at the center surrounded by a disk. But in the context of today's discussion, we are interested in exploring the star clusters, some of which are present in the disk, while others, called the globular clusters, surround the galaxy as shown here. Star clusters can broadly be classified into two categories, the open and globular clusters. The open clusters contain a few hundred to 1,000 stars, are less than 10 parsecs across, and are found in the plane of the galaxy's disk. Open clusters are young, which means they have young stars and therefore may contain dust and gas produced during star formation. The globular clusters, on the other hand, contain 10 to 100,000 stars, are much larger in size, about 20 to 100 parsec in diameter, and are located outside the galaxy. Globular clusters are very old systems and hence contain little or no gas and dust. It is important to know about the star clusters because they may sometimes be misidentified as dwarf galaxies. With that information in hand, let's now move to the dwarf galaxies. Just like their giant counterparts, the dwarf galaxies can also be classified into multiple morphological classes based on their appearance. Irregulars, dwarf ellipticals, dwarf spheroidals, blue compact dwarfs, and of course, the dwarf spirals are some of the common terms used in the literature to describe these little systems. The dwarf ellipticals are a scaled-down version of their giant counterparts, and just like the bigger ellipticals, are mostly found in the centers of galaxy clusters and larger groups. The dwarf spheroidals are very low luminosity galaxies composed of old and intermediate age stars. Usually, they do not contain any gas. Many of the satellite galaxies of the Milky Way are dwarf spheroidals. Given the extremely low mass of dwarf spheroidals and occasionally other types of dwarf galaxies, they may intuitively appear as the scaled-up version of star clusters. However, this is not entirely true. Even if the mass range of massive star clusters and very faint dwarf spheroidals overlap, the dwarf galaxies are not just much bigger but also have multiple stellar populations. On the other hand, all the stars in a star cluster form together. In other words, despite similarities in appearance, luminosity, and mass, star clusters and dwarf galaxies have evolved differently since their formation. Next in line, we have the irregular galaxies, most of which have stellar masses less than about 1 billion times the mass of the Sun. The dwarfs are mostly star-forming galaxies with a lot of young stars and gas in them. Despite similar morphology to the dwarf spheroidals, the blue compact dwarfs, or the BCDs as they are commonly known, are extremely blue star-forming galaxies associated with the presence of a lot of gas. Morphologically speaking, sometimes they are also referred to as the blue spheroids in the literature. These systems are a relatively new discovery and are very interesting objects. Let's dive a little bit deeper into their properties. A few years ago, we studied a sample of more than 400 galaxies in the local universe in order to explore the properties of the blue spheroids. As shown here, the blue spheroids have optical colors similar to the spirals, but they still look like ellipticals. In fact, the blue spheroids seem to follow the color magnitude relation shown by the large spirals and ellipticals. They also appear to be smaller than other dwarf galaxies of same luminosity. Such relations are used as an evidence to suggest that the blue spheroids have evolved like the disk galaxies. Besides the physical appearance, some other properties of blue spheroids are also correlated better with spirals. For instance, here the rate of formation of stars is shown as a function of their magnitude. It is quite obvious that the blue spheroids follow the same trend as observed for the spirals, albeit with a large scatter, essentially showing that blue spheroids are morphologically similar to ellipticals but behave like spirals. Let us now move on to a very rare class of dwarfs called the ultra-compact dwarf galaxies, or UCDs. For quite some time, there was a lot of confusion regarding their status. That is, if they were globular clusters associated with the central galaxy in a cluster or actual galaxies. Careful and very modern observational techniques have now been applied to establish the status of these extremely bright and small systems as bona fide galaxies. Their origin is, however, still debatable. Many astronomers believed that they may form in tidally stripped tails of galaxies undergoing transformations due to the impact of the intracluster medium or interactions with other galaxies in high-density environments such as clusters. The UCDs are shown to follow the Faber-Jackson relation extrapolated to lower luminosities as shown here. In the Fornax cluster, the UCDs have much lower surface brightness relative to the core of the nucleated dwarf ellipticals. These observations evidently disprove the suggestions that UCDs are bright nuclei left over from the threshing of dwarf galaxies around the central dominant galaxies in clusters. Remember I said in the beginning that sometimes large galaxies can also be faint? Well, the ultra-diffuse faint galaxies are a perfect example for this case. As shown, the UDFs can be as large as the Milky Way, yet have extremely low surface brightness like the dwarfs. While some initial studies suggested them to be rapidly rotating or puffed up versions of other low luminosity galaxies, recent data suggests that they are likely failed large galaxies, which means they are large systems which, for some reasons, failed to form the classical disk and bulge. As a consequence, they are some of the most dark matter dominated galaxies in the universe that we know of. The dwarf galaxies are often found orbiting bigger galaxies like the Milky Way. In an earlier video, I introduced two of the most famous satellites of the Milky Way, the Magellanic Clouds. The Magellanic Clouds are two of the many satellite galaxies of the Milky Way. They are orbiting our galaxy just like the Moon orbits the Earth. Besides the Magellanic Clouds, there are several other small galaxies orbiting the Milky Way. In fact, all of these galaxies, along with two other larger galaxies and their satellites, form a gravitationally bound system known as the local group. The local group comprises more than 120 dwarf galaxies and three massive galaxies, the Milky Way, M31 and M33. You may also note that the dwarf galaxies are not distributed randomly around the large galaxies, but in planes above and below them. This observation left astronomers puzzled for decades. In fact, the issue is still debatable, because if matter is accreted onto a massive central galaxy due to gravity, one expects dwarf galaxies to be attracted to the Milky Way from all the directions. In fact, Not just the Milky Way, but similar distribution of dwarfs is found around the Andromeda as well. Some astronomers believed that this preferential alignment of dwarf galaxies suggested that there is no dark matter. However, advancement in technology led to improved models of formation of structure in the universe, such as the study shown here. By tracking the dark matter particles in cosmological simulations, it was shown that rather than coming from all directions, matter accretes onto massive nodes through preferred directions and can indeed reproduce an arrangement similar to that observed in the local group. This is because all matter in the universe, visible and invisible, is distributed on a web-like structure. So dwarf galaxies travel towards the massive galaxies along large-scale filaments. As a consequence, the larger distribution of matter appears like a massive pancake of matter rather than a spherical ball. Let's briefly talk about the dwarf galaxies around the Milky Way. As you may notice, in these composite images, these systems are very faint and very closely resemble star clusters. But in fact, they are very different from the globular clusters as shown in this plane, mapping the V-band magnitude as a function of radius. This evidently shows that globular clusters are different from dwarf ellipticals. Another interesting correlation of sorts is found between the surface brightness and luminosity of dwarf galaxies in the local group. In this figure, the top panel shows the central surface brightness, whereas the bottom panel uses the average surface brightness within the half-light radius. In simple terms, surface brightness is the luminosity of a galaxy per unit area. The half-light radius is the angular size from which half of the total luminosity of the object is received. The central surface brightness is in principle more susceptible to localized features such as nuclei, individual bright stars, etc. present in the center of a dwarf galaxy relative to the effective surface brightness. But irrespective of the measure of surface brightness considered, galaxies brighter than V-band absolute magnitude of around -9 show a correlation between luminosity and surface brightness. In fact, galaxies fainter than absolute V-band magnitude of around -8.5 mag have remarkably similar surface brightness despite a change in luminosity by a factor of around 600. This is therefore a hot topic of debate. It is also found that dwarf galaxies closer to larger galaxies such as the Milky Way or Andromeda severely lack hydrogen gas, while the fraction of gas mass per unit luminosity increases further away from the larger neighbors as shown here. The dynamical mass of dwarf galaxies in the local group also correlates with their absolute visual magnitude across a factor of nearly 1 million in luminosity. Using radio telescopes in the early 1970s, astronomers discovered a stream of gas called the Magellanic Stream associated with the Magellanic Clouds. But the 50-year-old mystery of the origin of this gas tail could only be solved recently using data from NASA's Hubble Space Telescope. Astronomers have now confirmed that most of this long ribbon of gas stretching nearly halfway around our Milky Way galaxy was stripped from the small Magellanic Cloud about 2 billion years ago, and a second region of stream originating more recently from the Large Magellanic Cloud. But the Magellanic Stream is not unique. In the past few years, astronomers have identified several such streams around the disk of the Milky Way. While most of them come from dwarf galaxies which were disrupted in the gravitational field of the Milky Way, others come from star clusters. As stars move through our galaxy, their position in the sky change over time as shown in this movie created using observations of the Barnard star taken at an interval of 5 years. The movement of a star across the sky is called proper motion. The proper motion provides 2 out of the 3 components of a star's true velocity. The third component is radial velocity, the movement of the star towards or away from us, which can be inferred from the red or blue shift in its spectrum. The most significant advancement in these studies come from the data taken by the European Space Agency's Gaia satellite, launched in the year 2013. Gaia is creating a very precise 3-dimensional map of more than 1,000 million stars throughout our Milky Way galaxy and beyond. Gaia is not just mapping their position, but motions, luminosity, temperature, and composition over and over again to achieve a very high level of precision in these measurements. These data help astronomers correlate stars physically, chemically, and dynamically to identify their membership to particular streams and therefore their origin. Dwarf galaxies are present at all redshifts, but are difficult to observe due to their small angular size and faint luminosity. Even if we see them, we cannot yet explore them in great detail like the dwarfs around the Milky Way. But better observing techniques and facilities are now shedding new light on their properties. Briefly, we discussed that they can form in the gas tails stripped from large galaxies in clusters. And here are some more examples to convince you of that fact. Using far ultraviolet data from the Ultraviolet Imaging Telescope on board the AstroSat satellite mission, we recently discovered many interesting objects in clusters which could potentially be progenitors of dwarf galaxies. For instance, in this image, you see the far ultraviolet FUV image on the left and the contours of the FUV image overlaid on the optical image of the same region of the sky on the right. Note that the bright blob seen on top has no corresponding emission in the optical image. This is very interesting because this either means the blob is a faint galaxy being created from the gas expelled from the galaxy in the front, or it is just hot gas, which may in due course cool down and then form stars. The arrow in the left image points in the direction of the cluster center, the most likely direction for a galaxy to be moving if it is under the influence of the cluster's gravity. As a consequence, the gas removed from it is expelled behind the galaxy, just like the wake of fuel exhaust from a speeding vehicle. In another project, we studied a very interesting spiral galaxy in a cluster which shows knots of star formation in the front, the direction facing the cluster center towards which it is moving. It also displays a wake of gas behind it as shown in red here. This galaxy, called the UGC 10420, also shows knots of blue star-forming regions in the tidal tails behind the galaxy. A closer analysis shows these knots of star formation shown in blue here are statistically different from similar regions found in the main body of the galaxy displayed as black circles, and that they may in future become new tidal dwarf galaxies or ultra-compact dwarf galaxies. In another study, it was found that various classes of dwarfs follow the size-luminosity relation obeyed by the larger galaxies as shown here. Note that even within this distribution of morphologically segregated galaxies, the BCDs fell in line with the large red ellipticals, whereas the star-forming dwarfs such as irregulars were closer to the spirals. Following the same trend, the star-forming dwarf galaxies overlap with the spirals in this plane mapped by the star formation rate of galaxies as a function of their stellar mass. In terms of environment, again, the dwarfs outside the local group behave similarly to the ones in the local group. These two images show the contours for the number density of galaxies in the Coma supercluster, which is at a distance of around 100 megaparsec from us. It is immediately noticeable that the color contrast here is striking. While one image is very red, the other is very blue. And this is phenomenal given that the color scheme in both is the same. The color here represents the fraction of star-forming galaxies in these regions. The top image is for the giant galaxies and the bottom one is for the dwarfs. So these images essentially show that the giant galaxies are not forming many stars irrespective of their environment, although their capacity to form stars is worst hit in the densest regions of space at the centers of clusters and groups. The dwarfs, on the other hand, are always star-forming irrespective of environment, except when they are in very dense regions. To summarize, today we discussed about the types and properties of dwarf galaxies and how are they different from star clusters. We also learnt about their interaction with their larger neighbors, finally concluding with the evidence of some formation mechanisms of dwarf galaxies in galaxy clusters. I hope you learned something new today. Do let me know in the comments what other topics would you like me to cover on this channel. I'll see you next week. Until then, take care.